Hey there, this is the lecture for section 5.5, right triangle trigonometry. All right, so in 5.3 and 5.4, we've been looking at the trig functions as they're defined in relation to a circle, usually even the unit circle. Now we're going to add a little bit to that. We're going to define trig functions based on the ratios of sides of the triangle. Okay, so you may have heard SOHCAHTOA. That's an acronym to help remember the trig definitions for the sine, cosine, and tangent. The definition for the sine of angle theta, this is theta right here, it's going to be the length of the opposite side of the right triangle that it sits in over the hypotenuse of that triangle. Right? The cosine is going to be the ratio of the length of the adjacent side to that angle, the adjacent side of the triangle over the hypotenuse. And then the tangent is defined as the opposite side over the adjacent side of a right triangle. All right, so this acronym SOHCAHTOA helps you remember it, right? Sine is opposite over hypotenuse, right? So we could say sine is opposite over hypotenuse, right? Cosine is adjacent over hypotenuse. I'm just abbreviating those. And then the tangent, right, is the opposite side over the adjacent side. Anyway, so it really isn't that different than what we've been looking at, right? Because if I take this right triangle and I put it inside a circle, it's exactly the same thing that we've been talking about, right? So if I could draw a circle, it would help. Let me try that again. That's not much better. Anyway, pretend this is a circle sitting on the origin, like we've been using, okay? We can see that we've been talking about these trig functions in the unit circle anyway, as cosine being the x-coordinate and the y-coordinate of this terminal point. We've been talking about the ratios with these trig functions. If it terminates at x and y, the sine was y over the hypotenuse, which in circle geometry we call that the radius, right? So it was y over r, right? The cosine was x over r. Look, x is the length of that adjacent side over the radius. So it's really just the same thing, right? Tangent was y over x, which is the same thing as opposite over adjacent, right? Because that opposite side, that length, is going to be the y-coordinate of the circle that it's in. All right, so given those new definitions, though, let's see if we can identify the sine and cosine of angle alpha, as well as the sine and cosine of angle beta in this right triangle that I've drawn here. All right, I don't know that angle, but I don't need to know the angle measure to find the sine and cosine, right, now that I know the ratios. All right, the sine of alpha, let's see, here's alpha right there, right, that's going to be the opposite side over the hypotenuse for this triangle. The opposite side of alpha is 4, and the hypotenuse is 5. All right, the cosine of alpha is going to be the adjacent side over the hypotenuse. And for this triangle, the adjacent side to alpha is 3. Of course, the hypotenuse is 5. Right? Now let's look at angle beta. All right, the cosine of angle beta is going to be its adjacent side over the hypotenuse, right? Which would be 4 over 5. And the sine of angle beta is going to be the opposite side over the hypotenuse, or 3 over 5. All right. Now, do you see something interesting here? A little bit of a pattern. Look, the sine of alpha and the cosine of beta are the same, right? The sine of beta and the cosine of alpha are the same. And in fact, this is always going to be true. Oops. This is always going to be true for the two angles in a right triangle. Okay. All right. So let's look at some applications, how we use this trigonometry in the world. This gets a little bit more interesting. Oop, come back. There we go. All right, so the angle of elevation to the top of a building in Seattle is found to be 2 degrees from the ground at a distance of 2 miles from the base of the building. All right, so let's draw a little diagram. If I've got, say this is my building, 2 miles, that's pretty far away, right? So make this a really long triangle. There. Okay, I've made a right triangle here. We'll pretend that building is perpendicular to the ground, right? And here's the point where we are away from that. And the angle of elevation, that means the angle from the horizontal moving up. So that would be this angle right here, this tiny little angle here, and that's going to be 2 degrees, all right? And this place is 2 miles away, so that means the horizontal leg of that right triangle is going to be 2 miles. All right, so use this information to find the height of the building. All right, so what's the height of the building? Let's just call it h. That's what we need to find. All right, so I can do that using sine, cosine, or tangent. Now, if I use the sine or cosine, though, I'm going to need to know the hypotenuse of that triangle, right? With the tangent, however, I don't need it. So let me choose to use the tangent here. The tangent of 2 degrees as opposite over adjacent, right? That's going to be h over 2. All right, solving for h, well, that's easy enough. We just multiply both sides by 2. So h then is going to be 2 times the tangent of 2 degrees. And let's see what that is. If, there, came on, 2 times the tangent. Oh, and by the way, be very, very careful when you have to use your calculator. Make sure that you're in degree mode if you're dealing with degrees, or radian mode if you're dealing with radians. It's one of the most common mistakes that I see in this class is forgetting which mode you're in. Keep hitting the wrong things. I'm sorry, guys. I don't know. I'm standing at a funny angle. Let's get back up there. Okay, here we go. And then where am I? There. All right, so let's check the mode. I am in degree mode, so I'm good. All right, if I'd been in radian mode, I would have needed to switch that. All right, so 2 times the tangent of 2 degrees. There it is. It's a decimal. It's a pretty small decimal. Point, what was it again? 0.6984 and some more. More decimals. Now that's kind of weird, isn't it? What are the units? Well, it's in miles, right? That's kind of weird, isn't it? Would we really want to specify the height of a building as 0.0694 miles? Probably not. We probably would want to express that as feet, right? So we should probably convert this answer to feet. However, I rounded that. I had to truncate some decimals, and I don't want to just apply a conversion factor to this decimal. I think I want to go back and recalculate that using feet instead of miles, right? So let me convert these miles over to feet. Let's see. I think there's 5,280 feet in a mile, right? So this distance in feet is going to be 2 times 5,280, right? Or what is that? 10,560? I'm sorry, not 10,000. Yeah, that's right, 10,560 feet. All right, let's run this calculation with feet. So instead of 2, we're going to use the feet. 10,560 times the tangent of 2 degrees. And this will tell me how tall that building is in feet. 10,560 times the tangent of 2. There it is. 368.8, we'll say. Okay. So if you ever, if you're out and about, have you ever seen guys with like something, or girls, or just somebody with a tripod and some kind of a device on top? A lot of times what they're doing is they're using a surveyor, and they're actually recording. They're actually recording angle measures and some different things, and they're going to use that to calculate maybe a distance. All right, so this is done. This type of trigonometry is done frequently. Let's look at one more. This one's a little bit more challenging. Let's see. We have a 400-foot tall monument, and it's located in the distance. All right, so let's make our monument. I'm going to say there. That's my monument. All right, and it's 400 feet tall. Okay, now from a window in a building, a person determines that the angle of elevation to the top of the monument is 18 degrees, and that the angle of depression to the bottom of the tower or monument is 3 degrees. All right, so how far is this person from the monument? All right, so angle of elevation, we were talking about that, but this is not the angle of elevation from the ground, is it? It's a window in a building, right? So let's see, we've got some building over here, right? And let's put the ground in. There, that's the ground. Here's my monument or tower or whatever it is. The window, let's just say the window, is right there, all right? So the angle of elevation to the top of this monument is 18 degrees. So if I connect that window to the top of that monument, and I'm going to need to sketch in a horizontal here, because the window is up, not on the ground, it's up above the ground somehow, some distance. But if I sketch in another horizontal, then I can mark my angle of elevation as 18 degrees. Okay, now the angle of depression to the bottom of the tower is 3 degrees. All right, so let's connect that window to the bottom of the tower. There we go. Then that tiny little angle in here, I'm not going to be able to fit it, so let me write it like this. There, that angle there is 3 degrees. So there's a diagram. Always do that when you're trying to solve a problem. Have a visual to look at. Now, what are we supposed to figure out? How far is this person from the monument? So how far is that window from the monument? Well, the distance is going to be the length of this horizontal dashed line I put in there, right? So maybe we'll just call that what should we call it? Let's call that X, because it's horizontal, so I'm going to call that X. So the distance then from the tower to the monument is X, right? And what are we supposed to find? We're supposed to find the height of that monument or tower, whatever it is. Yeah. So how do we go about doing that? Well, if we want to use right triangle trigonometry, we've got to have right triangles. All right, that big triangle that I've drawn is not a right triangle. So let's go ahead and mark these two smaller triangles as right triangles. This is going to be a perpendicular. We're going to assume that monument or tower is perpendicular to the ground. All right. So now we've got two smaller triangles. We have the upper triangle and we have the lower triangle, but at least they're right triangles, so I might be able to use SOHCAHTOA on it, right? The problem is I don't have the length of any of the sides of these smaller triangles, all right? So I'm going to have to get creative here. I know that the length of the vertical side of the top triangle plus the vertical side of the bottom triangle is 400, right? So maybe I could measure the vertical side of this bottom, or I could label maybe the vertical side of this bottom triangle as Y, all right? And if I did that, then I could call the length of the vertical side of that top triangle 400 minus Y, right? At least I have something to call that. Now let's see if we can write some trig functions. Now again, I'm not going to go with sine or cosine because I'd have to find out the hypotenuse first, and I don't need it for the tangent, so I'm going to go ahead and use the tangent. So one equation that I can write here is the tangent. Let's do this angle in the upper triangle first. I can say that the tangent of 18 degrees is the opposite over the adjacent. Well, the opposite side we're saying is 400 minus y, and we're saying the adjacent side is x. Right? Now I can write a second equation, right, for the lower triangle. I can say that the tangent of 3 degrees is equal to opposite over adjacent, so that would just be y over x. So I have two equations. I can't solve either one of them by itself, but together I can make them a system of equations, and I can use one equation to solve the other one. All right. So look at this lower equation. That looks easier. So I think I'll go ahead and solve this lower equation for y because it just seems easy to do. I'll just multiply both sides by x. And now I have this expression for y, x times tangent of 3 degrees. All right. And I'm going to substitute that expression for y in terms of x into the other equation. Right? So let's rewrite that. Now I have the tangent of 18 degrees equals 400 minus, let's get this out of the way here, 400 minus, and not y, but x times the tangent of 3 degrees. And that's all over x. Now I have an equation that I can solve, right? All I need to do is get x by itself, and I'll have something I can put in the calculator and find the value of x for. All right, well, I better start by getting x out of the denominator. So let's multiply both sides by x, and they'll divide out. Now, I have an x term on the left and an x term on the right. I should probably move those two x terms together and get them on the same side, right? So I'm going to add x times the tangent of 3 to both sides. So I'll have x times the tangent of 18 degrees plus x times the tangent of 3 degrees, and that's going to be equal to 400. All right, now I can't really combine these without finding the values of the tangent of 18 and the tangent of 3. And I don't want to do that yet because I don't want to do any rounding. I want to keep every decimal until the very end. All right, so what I'm going to want to do then is I want to factor out that x. When I factor it out, I'm left with the tangent of 18 degrees plus the tangent of 3 degrees. And this is something that I could then divide away, and I will have an expression for x that I can put into the calculator. It's a lot of writing. Please divide out now. So let's put that in the calculator and let's just see what that is. If my calculator wake up. There we go. All right, 400 divided by, and I better put that denominator in parentheses, the tangent of 18 degrees plus the tangent of 3 degrees. Okay, and there's my answer, 1060, a little tiny bit of decimal, but I think I'll just truncate that. So it's 1060. What was our units again? We were in feet. 1060 feet. All right, that ends the lecture for section 5.5, the right triangle-based trigonometry.